dependence of number of scattered alpha particles in Rutherford experiment. Now in this we will study that what factors affect the number of scattered alpha particles. In Rutherford experiment, the scattered alpha particles were detected by Geiger-Marsden counter. On that basis, there was some factors which affect this number of scattered alpha particles. So first is the atomic number. Z. So now let us have that number of scattered alpha particle is equal to n. Let n equal to number of scattered alpha particles. So first factor that affect is the atomic number. Atomic number Z. So this number of scattered alpha particle is directly proportional to Z square. It means that larger the value of Z, larger will be the number of scattered alpha particle. So n1 upon n2 equal to z1 upon z2 whole square, and it gives you that n2 is equal to n1 into z2 upon z1 whole square. So number of scattered alpha particle is directly proportional to the square of the atomic number. Second number that we have the kinetic energy. Kinetic energy of alpha particle. This n is proportional to 1 upon square of the kinetic energy, square of kinetic energy. So now we can have that as the kinetic energy of the alpha particle increases, the n will decrease. So this as kinetic energy increases Z, this n decreases, or this kinetic energy decreases, then this n increases. So this we have that as the kinetic energy of the alpha particle is increased, the less and less alpha particle are scattered. It means that they pass through the foil without any kind of deviation. So now we can have that this n1 upon n2 equal to kinetic energy 2 upon kinetic energy 1. This is now whole square, or n2 is equal to n1 into kinetic energy 1 upon kinetic energy 2. This is now whole square. So with this help of this formula we can find the the number of alpha particles scattered at the different energies. Now number 3. Angle of scattering. Angle of scattering. Now what we have, that this is suppose the nucleus, this is the alpha particle that is coming here and it is being scattered in this direction. This is now your alpha particle, this is now also the alpha particle, and this is being scattered at angle theta. This is now angle of scattering theta. Similarly, if we are having here, the alpha particle will be scattered in this way. This is being scattered at this angle theta. So this theta is the angle of scattering. This is now alpha particle. Alpha particle. This is now alpha. This is now also the alpha particle. This is alpha particle. This is now alpha particle. So now it is found that this n is proportional to 1 upon sine to the power 4 theta upon 2. It means that as the angle of scattering increases, the number of scattered alpha particle decreases. So now we can have that this is angle theta and this is now number of scattered alpha particles on this axis. Then this is the initial number of alpha particles, so they will decrease like this. This will be the graph. That is the variation of this scattered alpha particle with the angle of scattering. So it can be have that this n1 upon n2 is equal to sine theta 2 upon 2 upon sine theta 1 upon 2. This is now raised to power 4. This is raised to power 4. So now we can have that as theta increases and decreases, as this is clear from this graph, or this theta decreases, then this n increases. So depending upon the angle of scattering, the number of alpha particles scattered that also are different at the different angles. So we can see from here that if theta is equal to 180 degree, then this is now pi by 2 and sin pi by 2 equal to 1. So this n is equal to have some value. This is the least value. So minimum angle of diffraction may be 0 and maximum angle of scattering may be 180 degree. So maximum value of theta, or firstly let us say minimum value of theta equal to 0 degree. It means that the alpha particle passes without any kind of scattering, so they pass at 0 degree scattering, and maximum value of theta, this is equal to 180 degree or pi रेडियन. इससे अधिक ये वैल्यू नहीं हो सकती है, बिकॉज इफ सपोज दिस थीटा इज मोर देन 180 डिग्री, इट मीन्स दैट दिस फैक्टर विल बी नेगेटिव, बिकॉज द For the angle greater than 180 degree, the value of sine will be negative, and for that one, this n will be the negative one. So it means that this cannot be held, that the angle of scattering may not be greater than 180 degree. Though this is raised to sine raised to power 4, so this makes all the negative numbers to be positive, but even now this n cannot be have the value, the theta cannot have the value more than 180 degree. Now fourth factor. Fourth factor is the distance of the target from the detector. Distance between target and detector R. तो इसमें होता क्या है कि ये गोल्ड फॉइल है, सपोज दिस इज नाउ गोल्ड फॉइल, दिस इज गोल्ड फॉइल, यहाँ डिटेक्टर लगा हुआ है, दिस इज नाउ डिटेक्टर, दिस इज डिटेक्टर. ये गोल्ड फॉइल है. तो इनके बीच की डिस्टेंस ये आर है, दिस इज नाउ आर. तो डेफिनेटली यहाँ से जो पार्टिकल स्कैटर होगा, इसको यहाँ तक पहुँचने में हो सकता है बहुत सारे पार्टिकल इसमें ऐसे हों जो दैट में बी एब्जॉर्ब बाय द मीडियम, क्योंकि यहाँ पर जो मीडियम होता है वो मीडियम इन अल्फा पार्टिकल्स को, जो स्कैटर्ड अल्फा पार्टिकल हैं, उनको ये एब्जॉर्ब कर सकता है. तो जब एब्जॉर्ब कर लेगा तो जो पार्टिकल स्कैटर हुए हैं वो डिटेक्टर तक पहुँचेंगे ही नहीं. परिणाम क्या होगा? दैट दिस विल डिटेक्ट लेस नंबर ऑफ अल्फा पार्टिकल्स. सो व्हाट वी हैव, दैट दिस n is proportional to 1 upon r square. सो ये डिटेक्टर जितना निकटतम होता है, क्लोज होता है इस गोल्ड फॉइल के, that will be the number of alpha particles. So this is why that the detector is placed very close to the target. So this n1 upon n2 is equal to r2 upon r1 whole square, or n2 equal to n1 into r1 upon r2 whole square. So by this formula we can find that if suppose distance is increased, then what will be the effect on the number of detected scattered alpha particle by the detector. Now number 5, thickness of gold foil. Or target. Now what happens, that if suppose the thickness is increased, it means that number of atoms per unit volume are being increased. When the alpha particle goes inside the gold foil, then it strikes or it collides with the atoms, and there it loses the kinetic energy. In experiment, it is supposed that the alpha particle do not lose its kinetic energy. So for that purpose, the gold foil must be as thin as possible. This is why that gold foil is preferred in Rutherford experiment, because gold foil can be is very much malleable, so it can be easily transformed into a very thin foil. So now what we have, that as if the thickness of gold foil is increased, the alpha particle the incident alpha particle will collide with more number of gold atoms inside the foil, thereby losing its kinetic energy. Losing its kinetic energy. अब ये kinetic energy लूज कर देगा तो क्या स्कैटरिंग होगी नहीं इसके अंदर. The alpha particle will not be scattered because this will be absorbed by the foil. So what we have, that the foil must be as thin as possible. If thickness of gold foil is enough, the alpha particles is enough. The incident alpha particles will be absorbed inside the gold foil and hence no scattering. No scattering of alpha particles. So the thickness of the target also have an important role in the scattering of alpha particles. So the foil must be taken as thin as possible so the alpha particle could not lose their kinetic energy and it strikes as minimum as possible with the atoms inside the foil. Because of that it will be scattered more and more. This is why that gold foil was preferred by the Rutherford in his experiment. Though he conducted his experiment by with the number of metals like aluminum, silver, etc. But he found that only the gold is more suitable element for the scattering of the alpha particle. So these are the factors that affect the number of scattered alpha particle in Rutherford experiment. Thank you very much.